Where are we? Oh, we're showing that. Can we turn it off?
You have to.
How does the, like, how do you get that much accuracy?
So we wanted to say hello and thank you for
It's so small.
joining us today.
Differences must be
Did you have a grant due at 5?
I have no
Today?
idea. I'm not an engineer and I don't care.
Say that again. I didn't catch what you said.
You have a grant proposal due at 5? Today?
We had a proposal due today. Yes.
You are very tired, are you?
I have no idea.
Well, Mike Snow did most of the work, so it's we were working until 5 p.m. just to submit on time. But Mike really and Laura actually they did a lot of work. So.
That's what he told us. So we are very grateful that you are here tonight. Thank you so much for coming.
Oh, thank you for the invitation.
There are a few more people who have to join.
Yeah, yeah.
People in the
Yes.
room. We're gonna get started.
Let me know. I'm going to just make sure that screen sharing works okay, if you don't mind, before.
Yeah, please go ahead. Yes, we are able to see your screen.
Okay. All right.
Thank you for joining us again. We will start shortly. We are expecting about 10 to 12 to join, and we have 4 confirmed professors and beyond me. This one. I want to show more of this. Oh, that's oh, it's that one. Yeah. And how do you monitor them? I'm not sure. We can move it. Oh, from here? Yeah. Yeah, there you go. See? Oh, that's great. Yeah. Yeah, that's pretty good, is it? Yep. Very good. So.
Yep. You're getting me dizzy.
Sorry about that. Oh, Gerardo joins, then we should start here as soon as Gerardo. Yes. So I don't know, how do we know if anybody from Toronto or Austin is able to connect or cannot connect? You know, we don't know. They don't email and say, hey, I would like to connect, what's going on? No, so I joined the University of Toronto's Discord group, and I met with their president, and I shared the whole invite with them. And whether they come or not, we don't. Yeah, okay. So they might join us, and then there's also University of Austin. They're expecting a few students from there. Yeah, so that's the thing. Number of people in pizza, everyone is going to ask as many questions. More pizzas, more questions.
I think that's fair enough.
Yes.
Yeah.
So I'm wondering if you send me the pizza with Uber Eats or.
We will definitely, I mean, it's not a issue. Or we just show up at IUPUI. It's like an hour and a half away.
I'm actually at home right now. I just came home, so hopefully the dogs don't start barking.
I mean, I look at it this way, if they do, it's going to be recorded forever. See you later. We wait for 2 more minutes.
In the meantime, if anyone has any questions here before we start. Yeah, Micah has a question.
What is near field scanning optical microscopes and how do they work?
This is a technique. I'm not going to be talking about those today, but basically, suppose that you have a sub wavelength. Imagine a perfectly conducting screen, and then you make a hole on that screen, and that hole has dimension which is smaller than the wavelength of the light that you're sending. Then if you look into the far field, you don't basically see anything because this aperture being so small, you don't see anything. However, in the near field, there is actually a lot of intensity. And the near field basically means that you have to be at a separation which is on the order of the size of the aperture. So the relevant dimension now, instead of being the wavelength, which is the characteristic length scale in optics, becomes the size of that aperture. So then what you have is you have a rather bright source of light, which is on the dimension of the aperture. So you typically make apertures on the order of tens of nanometers, and then you can put your sample and illuminate your sample and do regular meaning anything that you can think about microscopy, polarization studies, or direct imaging, or spectroscopy, anything that you can think that you can do with light. You can now do it, but instead of the resolution being governed by lambda, it's governed by the dimension of the aperture. So you get an optical technique with a resolution which is similar to what you can get with scanning electron microscopy. Advantage is you don't damage your sample in general. I mean, any sample that it is okay under light, you can image and you're not going to damage. It's not always the case with scanning electron microscope because you're bombarding with electrons at kilo electron volts. That is the bright side of this technique. The downside is a scanning technique. I mean, scanning electron microscopy is also a scanning technique, but you can scan very fast an electron. This one is not so easy. You have to do raster scans, and it is rather slow. I mean, you can really struggle to get video rates. So it's a compromise, and so what happens is that it is a very, very useful for some applications, but most of the cases it's not used because it's really a lot of work to get it working, and the payoff is not that good. So,
Thank you.
Thank you so much.
All right, let's get started because maybe you want to wait. We can get started. I mean, yeah, they're on the house, then that's fine.
Yeah. Shall we get started?
all right.
Give me a second. So I'd like to introduce our guest speaker today. Today is Tuesday, February of 21. It's 7 p.m. Eastern, and we are here at Indiana University Bloomington. So this is the Quantum Technologies for Everyone Club. Now, we are a recognized student-governed organization at Indiana University Bloomington. And our guest speaker here today is Professor Ricardo Decca. He's from the physics department of IUPUI. He's a professor and department chair at IUPUI, and also the co-director of Nanoscale Imaging Center. He will talk about quantum hardware for quantum sensing and everything about quantum computing in general. Thank you so much for joining us, sir.
All right, thank you very much. Let me now share my screen. And thank you for the introduction. I actually, well, a few disclaimers. I will use a platform which is how to measure the gravitational attraction, the gravitational interaction in general, as an example to what we call, as you said, hardware for quantum sensing. And we can then have discussions if you like to do so. I mean, but I want to highlight through this example, what are the things you have to take into account when you want to do what we call a quantum measurement, and why sometimes it's better than a classical measurement, and how, in fact, you want to go beyond what is called the standard quantum limit, which I will describe throughout the talk. And as it was said, I'm in the Department of Physics of IUPUI, and this is this joint campus between Indiana and Purdue, but as you might be aware, very soon we are just going to be IUI. So Indiana and Purdue are splitting, and I guess after 50 plus years of marriage, they are going to call it quits, and physics will just be another, it will just be under Indiana and no longer Purdue. Anyhow, there is this word I'm going to present. It has different topics, but basically a bunch of collaborators, most of them from Europe or South America. By the way, I'm from Argentina. That is where my accent is from. And a group of students, I'm listing here graduate students, a former postdoc, Muchuan. We have now a new graduate student. She's just starting, so I didn't list her here because she still has not contributed to this work. And then what we do have is a lot of undergrad students actually working in the group, on the order of, at any given time, 4 or 5 undergrad students. Some of them working for a semester, some of them working for a few years. And the funding is mainly from National Science Foundation, but also from Department of Energy, Argonne National Lab, and also some internal funding from Integrated Nanosystem Development Institute here at IUPUI. And first of all, what we do is actually measure gravity, and just to put it in perspective, there are 4 forces. The strong, the weak, the electromagnetic, and the gravitational one. The strong, the weak, and the electromagnetic are put together in quantum electrodynamics. The gravitational force is too weak, cannot be unified. There are efforts for unification, and furthermore, it cannot. We don't know if it is if gravity has a quantum origin or not, and that is a part of the effort that we have. And typically, experiments that we do that we were doing up to now are basically depicted here in this panel on the left. We have a sphere which is small but macroscopic, 150 microns in radius, and we bring that close to our sample, and our sample is placed basically in this torsional oscillator, which is in blue here. And then we have some interaction, and that interaction causes a deflection in this oscillator. It's a force that causes a deflection, and then that is what we measure. Also, we do have things which are macroscopic, if you wish, which are basically we're trying to measure G with a conventional torsional oscillator, completely classical, although some of the measurements are not quite quantum, but basically using coherent detection on the system. But just to give you an idea, we have gaps here that go from on the order between the bodies between 0.1 microns to hundreds of millimeters. So the dimensions are from 0.1 to 100 millimeters, and we put it between 0.1 to 10 to the 6 microns. So there's a wide range of separations that we cover. And with these ones, what I'm going to be talking about today are basically effects that are really quantum in nature. For example, quantum friction. This is a purely quantum effect. There is no classical counterpart. It's not an extension or a semi-classical expansion of that you can do something classical and then do the quantification of that. This is a completely quantum effect. And then I was also spending a large time talking about the gravitational interaction. And as I was saying, is there anything more to it? Meaning, general relativity appears to explain it very, very well. But, we do expect that it needs to be quantized. And what can we do in order to address that? I'm going to burst the bubble. As of now, I don't have an experiment to go in one way or another, but we are starting to make headways into really have a desktop experiment that, given right conditions and developments, we could start saying something about the nature of gravity in the future, hopefully near future, but in the future. This is this new experiment I'm mentioning here at the bottom of the slide. So just to give you an idea, we have Newton's field equation here, and I have a different color coding, and everything that is in red is basically purely classical. So we have the stress tensor. which is purely classical, and that stress tensor basically reduces to Newtonian gravity when we're talking about small masses and speeds which are very far away from the speed of light. There's a G basically, if you work it out properly, what you will see that this basically tells you is a potential eventually, which is the 1/r potential that we learn in introductory mechanics. Yeah. And then we have a few other things, and one of these is this cosmological constant, right? This cosmological constant can come and gone, and what is the nature of that cosmological constant? Well, there are more leeways now, but this cosmological constant is unknown, or it was unknown to 120 orders of magnitude. So it's the blemish of all physics, I will say. Yeah, and then we have the fundamental constant, which is G, which is also embarrassing because it's the one that is known the least, and it is known the least, and basically CODATA, which is the conglomerate of let's say NIST and equivalent ones from industrialized countries. Every 4 years they get together and analyze what are the values of the constant that have been measured and adjust those constants, and then go ahead and decide, well, this constant is known so well that we're going to define it, as it has happened with the speed of light, with the Boltzmann constant, and so on. And so this is what it happens, and then we have this the mass distribution that gives this stress tensor T mu v, which is an energy momentum tensor. Yeah, and that is all quantum in nature. Everything that has to do with mass distribution is going to be quantum, and so we have the right hand side, which is quantum, the left hand side, which is classical. So there is something that clearly is not working here. So is this gravity really quantum in nature? Well, that is one of the questions that is out there. So it needs to be addressed. And what I'm going to try to show you is our basically attempts to be moving in that direction. Here in the left, at the bottom left, we have things that people has proposed to modify gravity. So suppose that there is either a gravity correction that is mediated by some boson that has it is light but has a mass, and then what I'm trying to show here is that this what is going to happen is that this is going to be corrected. The gravitational potential, the Newtonian gravitational potential, is going to be corrected by a IUPUI term, in which lambda is the h bar c over the mass of this the boson that mediates the interaction. And then alpha is some constant, which is just to compare this interaction with regarding to gravity. The part that is in yellow has been excluded by experiments. The part is that below that, and all these names that you have there are things that could be there, and we still experimentally we cannot rule them out. And what I want to bring your attention to is two things. Well, there are a lot of things here, but two things. If you go to basically something on the order of 50 microns or so, then we know that gravity is a good description, because this yellow here goes to alpha equals to 1, and so we know that gravity is a good description. But now if you go to lambda, which is at 10 nanometers, then you have to go in the vertical scale. This is a log scale, in the vertical scale to 10 to the 19. So we have excluded things which are 19 orders of magnitude stronger than gravity, and then we know that there is nothing there. But there are 19 orders of magnitude to go before we can tell that really gravity is a good description if lambda is equals to 10 nanometers. So my point here is that there is a lot of work to be done. What we're going to show with this experiment that we're trying to do is we're going to generate a mass that has different spatial frequencies, and I'm going to come back to this later on just to make it more clear. And we're going to have an oscillator, which is a quantum oscillator, and we're going to try to produce quantum transitions in these oscillators mediated by this gravitational interaction. And that is basically what is at the heart of today's talk. And what do we have to do in order to produce a quantum oscillator, and what will be the sensitivity of the quantum oscillator, and what are the things that you have to be careful about when you are trying to do this kind of experiments. By the way, if there are any questions, please I think it will be better probably if you interrupt me while I'm talking instead of waiting until the end. And I'm not monitoring the chat. So, I mean, if I see something popping in the chat, I will take a look, but I'm really not actively looking into the chat. So,
Okay, yeah.
Well, one thing that you have to be careful about is, for example, the fact that, remember, we're putting things that are going to be closely spaced together. And when you do that, you have a background that there is no knob for it. And that background is what is called the Casimir effect, and or the van der Waals, depending how close you put these two bodies. The bodies here are these two yellow plates, if you wish. And basically what this tells you is that in vacuum, the expectation value of the electric field, or the expectation value of the magnetic field, or the expectation value of the expectation value of the electromagnetic fields, the magnetic field A and the electric potential phi are zero. Yeah, those, I mean, it's vacuum, so you expect that to be zero. However, the expectation value of the energy that will go as a field square is not zero. And the expectation value of that field is actually, not only is not zero, it's infinite. In any cavity that you have, the expectation value is just the mode inside the cavity, not populated by, not thermally populated, just those 0 point energies associated with electromagnetic field is actually infinite. And the point is that, well, I mean, this is something that we don't have access to. We just put these two plates, the energy is infinite. We just produce a small change in the position of one of the plates, and then those changes, both, it's also infinite, in the new position is also infinite, but those changes are finite, and it goes as this force per unit area goes as 1 over the separation to the 4th power. So my point is that there are a lot of things that we have to be careful when we put two bodies in close proximity. One of them being these quantum-induced 0 point quantum-induced vacuum forces or vacuum interactions. So going back to this experiment that I showed you before, then what I want to show is that with our measurements, which again was using a classical oscillator, we glue a sphere to a classical oscillator, microelectromechanical system, and then we were able to do this curve here that you see as it says IUPUI 2014. But then we have a long way to go, and then we want to design things that are going to be better than what we did with these mechanical oscillators. So this is just to give you an idea of the experimental setup. We have this plate. This plate is just the old experimental setup. It's a plate, and there is a small gap here in the corner. There's a small gap between this false color image, this plate, and the electrodes underneath. And this is a torsional oscillator. This plate can oscillate back and forth along this line in the middle. And that is what we measure, just to give you an idea. This is what we learn using what are going to be the response of the oscillator. And this basically tells you what the limitation is. So if you work in resonance, and there is a quantum equivalent here, if you work in resonance, you basically get all the benefits of working of having a very high Q mechanical oscillator. If you move away from resonance, then the minimum detectable force becomes on the order of a pico-newton. But if you work in at resonance, the minimum detectable force is on the order of 1 femtonewton per square root of hertz. So this is just to give you an idea of what is the resolution we have with these mechanical, classically mechanical oscillator. We can measure forces on the order of, if we integrate for 1 second, we can measure forces on the order of 1 femtonewtons. Typically, these experiments you integrate for a long time, so on the order of 10,000 seconds. So we can measure forces which are basically maybe a factor of 100 better than that. But still, these are small forces, but they are very, very large compared with a typical gravitational interactions. Let's take a detour of this completely quantum phenomenon and how we are planning on measuring, which is also a completely quantum measurement. So there is this fact that if you have suppose that you have just a dipole, and if you have this dipole or a particle which can be polarized, right? That you can have an induced dipole in this particle, and then you're going to be moving this particle with respect to a dielectric. And when I say the dielectric, this means any material. And then if that material is a real material, so it has a dissipation associated with it, then what is going to happen is you have this picture that you have here on the top left. There is an image associated with this moving particle, but since the speed of light is finite, this image is lagging the position of this particle, and then since it is lagging the position of this particle, and remember now we have this vacuum fluctuation, so there is an interaction between the particle and its image, and this has two components. One component of the force which is perpendicular to the surface, and this is the regular Casimir-Polder interaction, and then we have another component of the force which is basically opposing the motion, and this is what we call the quantum friction. The way how we go about to solve for this is that then we have a Hamiltonian. We have this, basically what we're going to put is that this polarizable particle is just a two-level system. And the part of the Hamiltonian associated with that is this, any two-level system you can map into a spin 1/2 system. And then this is basically this first part of the Hamiltonian that we have in here. And then we have another part, which is the Hamiltonian associated with electromagnetic radiation. That is there, either you have the particle or not. And then you have the Hamiltonian, which is associated with the interaction. And that interaction is just a dipolar interaction. So this is a simple system, but this is how we model our system. And what happens is that this interaction modifies the state of the particle. This interaction is non-unitary. It's an interaction, basically vacuum acts as an open system. And so basically the states of this two-level system decays on the vacuum. And if you just concentrate on just the two-level system, what happens if you prepare it in one particular state, what is going to happen is that it will decay and eventually will decohere completely, and then you cannot show these states in this block sphere in which you have the ground state will be here, the South Pole, and the excited state will be the North Pole. This is prepared in some arbitrary state, but then you have different situations. But now what happens is under certain conditions, this decay is non-unitary, but the decay is slow. And that is the regime in which we want to put ourselves. So if we do that, what we have here is that then, yes.
Previous slide. What is the sigma z? That I'm not clear on that.
Say that again, please. I did not.
In the Hamiltonian equation, what is sigma z?
Sorry, I accidentally. Okay, what is sigma z?
Yes.
Oh, sigma z is just the Pauli matrix for spin 1/2 for spin 1/2. So this is a matrix which is a 1, 0, 0, -1.
Okay, yeah.
This is just a two-level system, which in reality is not a spin system, but as I said before, any two-level system can directly be mapped to a spin 1/2 system. Yeah.
Yes, thank you.
Okay. So then basically what we do is, well, going back to here, then basically if the transformation were to be unitary, you will have this, the interaction with a Hamiltonian and a system that is not vacuum, but is some control system. You can have, for example, have this precession denoted by the dotted line, right? And your system will precess and will basically stay there. And if there is no decoherent effects, it will always stay there, right? That, for example, if you put this into a magnetic field or something along those lines. However, with vacuum, but with a small interaction with vacuum, you can have something which will look like the blue line. And basically what it will get is you will have an extra dephasing. And that extra dephasing is what we are plotting here. And what we're plotting here is what will be that extra dephasing. And I'm comparing here two terms. On the vertical axis, we have the external dephasing when you have a velocity, a relative velocity, compared with the external dephasing that if you don't have any velocity. So if you don't have any velocity, you will have also some dephasing, but we're comparing that. And n is basically the measuring in some characteristic time given by the energy gap between your two-level system. And what we found, and this is not an exhaustive search, what we find is suppose that you use n-doped silicon, at a characteristic doping level, which is on the order of 10 to the 16 impurities per cubic centimeters. So it's a doping level above the metal insulator transition for silicon, but it's not a huge doping level. And you put that your two-level system is an MV vacancy, you get this red curve here. And so what this is telling you is that you have 300 steps. If you can do 300 oscillations, then this extra phase that you get is 2 pi. So basically, this is something that actually we could measure. So similarly, if you look into the right-hand side, this is basically the terms that is going to tell us if you do the expectation value modulo square of the ground state, this vacuum interaction because it's moving, and the excitation state, once again, at constant velocity u and at velocity equals to 0. If you do that, what you see that there is a huge change in this rho 1, 2 term if you use these N-silicon with a nitrogen vacancy. And there are some other terms here, which are, for example, N-silicon with a rubidium atom, or gold instead of silicon with an NV vacancy, or gold with rubidium. So of these 4, more or less standard candidates, clearly the NV vacancy is the best one. So that is what we're trying to do. What we're trying to do is design an experiment that will allow us to do these measurements. And for reasons that we learn in our classical measurements, we know how to rotate things very, very fast and very, very stable. I'm not going to get into details, but and these measurements, you will say, well, but this is not the same as moving one body with respect to the other one in an inertial frame of reference. This is non-inertial. It is true, but for all practical purposes, the effects of dephasing associated with non-inertial frame of references are very, 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 very small, so we can really disregard them. So what we do then, basically, we put this MV center in basically in the tip of of a modified AF atomic force microscope, very close to the surface, in a gap which is on the order is less than 10 nanometers separation gap. And the reason of this having to be so small is because these quantum friction changes as the separation between the two bodies to the 10th power. So as soon as you move away just a little bit, if you go to 20, if you go from 10 to 20 nanometers, these forces changes as 1 over 2 to the 10th power. So actually, it's basically there is nothing after you go away from more than 10 nanometers. There is nothing. In fact, we are not measuring the force because this force is basically very, very small. That is what the reason why instead of measuring a force, we're measuring the effects that this has in the phase of the quantum state of the two-level system. Again, it's a completely quantum measurement. What is the phase induced in the state that we are generating? And the state we're generating again is a typical state in the MV vacancy. So we have this scheme here, and what we have is we have the ground state and the excited state, and those are the ones that we are addressing. Again, there is an optical system in which we address, and we take a look, for example, in the luminescence of the system, and these transitions are all in the gigahertz range. So we have to produce, or we have to use a microwave electromagnetic fields in order to produce the transitions. So basically, we have shown that we do have a system, a two-level system, that it is a quantum in nature, and now we're trying to actually do this measurement just to show that for the first time, this quantum friction can be addressed. And again, what I'm trying to emphasize here is that the phenomenon is purely quantum. There is no classical counterpart of friction in vacuum. If you move, if you do a classical description of vacuum, if you wish. And furthermore, what we're using for the detection is a purely classical, purely quantum system, which is this MB center and the superposition between the ground state and the excited state in this MB center. And the techniques that are used, for example, just to give you an idea, what we do here is you prepare the system in the ground state, then you produce what is called a pi/2 pulse. This will put your state from the ground state into this, let's say that you do a pi/2 pulse and send the system into the X state. This is this first pulse, which is this light blue pulse here in figure A that I have on the transitions. So you have that transition, and then you wait a given time, whatever time you want to wait. And then what is going to happen is that there are dephasing mechanisms inside the system, and then this state that now is a superposition and equal superposition of the 0 and 1 state will dephase in the equatorial plane of this Bloch sphere. Then what you do is after this time t/2, you produce a pi pulse, so it will send everything from something that, let's say, the state in X will go to negative X, and everything that has dephase will also go to the other direction. And then you wait again a time t/2, and then whatever before was, let's say, that it was causing a dephasing going from the state X to something that will have a component along Y. Now on the other side, it will actually bring it back to the negative X direction. So this one will come back to to something that will be more or less better cohere if it is a quantum interaction. And then what you do is you do another pi/2 pulse that sends it back to the original point. So everything that was quantum in nature with this pi pulse, you send it back to so you make it cohere again, and then everything that is not quantum in nature, right, interactions with an open system, a classical field, will produce a decoherent, and that is what you measure. And then what happens with these, the good thing about these MB centers is that that has a very long T2, a very long coherent lifetime. As you can see here, is on the order of milliseconds. And milliseconds is a very long time. You can do a lot of things in milliseconds, right? You are addressing these things in microseconds. You can address it multiple times. And in fact, this is such a good system that it has been proposed and tried to build a quantum computer using MB centers. Yeah? So you cannot put too many qubits with MB centers, but just to give you an idea that it is a good system to work with. So we are currently working on this and actively trying to build this system. And so that is something we are working on. I want to also show you, I will skip this part, but say it again.
We have a question in the
previous okay.
Yeah, I'm not sure if you can hear me from over there. If not, then
can you hear the person?
I can hear you.
Okay, yes. What method do you use for the state preparation before you do your pulses, your pi/2 pulses?
For the separation measurement?
What method do you use for state preparation? That first portion where you use the laser and the green. Do you do optical?
Actually, to prepare it in the ground state is actually relatively easy if you wish. You can do two things. One thing that you can do is directly wait, because then the system will go to the ground state with a quite large fidelity, because the energy difference between the ground state and the excited state is significant. So you can just wait and let it sit at the ground state. If not, what you can do is you can basically address it with light, and then basically what you do is you produce an excitation from the ground state, and from the ground state, you can produce an excitation to here, what I call ground to the excited state. And then what you can do is you can drive that directly to the ground state. If the system was already excited, with you produce a resonant driving that will drive it into the ground state. And if the system was in the ground state, you excite it and then force it to decay. Yeah. So it is an all optical addressing, which basically sends the system into the ground state if you want to have a higher fidelity on your preparation. Yeah.
Thank you.
Sure. So I'm changing completely gears, and I'm going to go now to these quantum measurements in the gravitational realm, if you wish. What we're going to be using here is something which is basically optical trapping of a nanobit. So the idea is exactly the same as we were using before. We're going to have a spring, and that spring is a good transducer for an interaction, except that different from before, that spring was completely classical, so basically dominated by thermal noise. What we're going to do now is we're going to isolate the system enough and cool it down enough in such a way that we'll be able to access the quantum nature of this spring. So particles have been trapped, and here you have in the left panel a good description of what things can be done. And particles have been trapped from basically particles that are rather large. You can trap particles which are on the order of hundreds of microns. And then all the way down to very small particles which are on the order of a few nanometers in radius. And there are payoffs that you have to pay in either one of them, and you will see that particularly when you want to detect gravity, you would like to trap a particle which is very, very massive. But remember, you have to put it into this quantum state. So there is a limit that you have, that there is there on how large a particle you can trap. Now, we can trap this particle, and for trapping, we use this optical trapping, which basically means that you have a very tightly focused beam, and in this very tightly focused beam, the particle, the minimum on the electromagnetic potential happens at the focal spot of the laser. And basically, you have a degenerate oscillator along the radial, so the direction perpendicular to the propagation of the laser, and a slightly less tight spring, or a spring with a smaller spring constant along the direction of the propagation. And typically, just to give you an idea, this is typically a factor of 2 difference. But then what you need to do is you need to cool it down. And here comes the first thing that is sort of surprising, or not necessarily surprising, but if you completely isolate your particle, so basically there is no energy flow from your system to the outside, well, you cannot cool it down. So you need to have some method of letting the energy, intrinsic energy of your particle, when you trap it down, go to the outside. And there are 2 typical approaches that you use. One of them is parametric cooling, which I'm going to try to give an idea of what that is. And the other one is called, you put your particle, you trap it, you do parametric cooling, then you put it in a cavity, and then you do cavity cooling. And I'm going to try to describe both because we are, in our approach, we are going to be using both. Parametric, so basically what we want to do is, just to give you an idea, we want to basically, here is a harmonic oscillator. This is a representation of what the harmonic trap from electromagnetic radiation is, and we want to actually see these states in this harmonic trap. The fact that it's a harmonic trap is actually a lie. It is a trap that it is harmonic if you're very close to the minimum, but if you go very soon, it is not that you have an infinite number of states. Depending on the trap that you can have up to 10 states, and very quickly this separation between the states is not really constant. It becomes bunched up together as you move up. But just to give you an idea, I'm going to say that it is a harmonic trap, just to give a frame of reference. And what you need to do is you have this characteristic frequency on the system, and this characteristic frequency will depend on how tightly focused your laser is and how strong your laser, what is the power of your laser. The point is, here comes experimental problems, right? What you will say is, well, I mean, if you're going to have to cool it down, what you need to have is you need to have the temperature of the center of mass. So how much these particles move in this harmonic potential, the temperature of the center of mass, the energy associated with the kinetic energy of the center of mass has to be much less than the separation between the levels. So what you will say is, well, you have to cool it down, but also the other thing you could do is, as well, use a more powerful laser, more tightly focused, powerful laser, and that's it, right? Not so fast. What happens is that you have a particle, which is a dielectric particle. You use a laser, and this laser is at a wavelength in which your particle is transparent, but nothing is absolutely transparent. So what happens is that any particle that you use, let's say you use a piece of glass, right? That glass is transparent. Well, that's true, but glass has defects. And then what is going to happen is that it doesn't matter what wavelength you use, this glass will absorb some light. It could have an absorptivity which is very, very small, 10 to the minus 10. This is very, very small. The best materials we can make that are going to be transparent have absorptivities on that order. Now, what happens is that every so often, your dielectric particle will absorb light. And then this light, basically what it does is just increases the temperature of not the center of mass necessarily, but the internal temperature of your particle. And what is going to happen is that unless you dissipate that energy, your particle gets hot. Now, the only mechanism that you have for dissipation, these experiments are done at ultra-high vacuum, the only mechanism they have for dissipation is radiation. And now you have a sub-nanometer particle. Somebody was asking about near-field effects. This is basically a near-field effect. The radiation into the far field is basically zero. So the radiation that you can have from this particle is basically very, very small, and your particle gets very, very hot. It gets so hot that if you don't have any ways of dissipation, you melt your particle. Literally melted. The internal temperature of your particle becomes thousands of degrees Kelvin because there is no way for that energy to go anywhere. Luckily enough, we have a way around it, and I'm not going to enter into details, but the particle we use is a quantum dot. And then what we do is we do what is called optical refrigeration. Simultaneously, as we trap our particle, we try to excite our particle, but with an energy, this epsilon excitation, which is not enough to produce an exciton in our quantum dot. In order to produce that exciton, we need to borrow a vibrational degree of freedom from our quantum dot. And then what happens is that those decay internally into the quantum dot in something we call a surface state, and then emit from that state. And emit with an energy which is this blue energy here. So imagine what happens. You excite with this excitation, which is in red, emit at a higher energy. In every process that you do that, you're cooling down your dot. And so basically what you're doing is you're removing this energy. Instead of melting your dot, you're providing an extra channel of dissipation in order to cool down the internal temperature. This is not the cooling that we're talking about in order to go into the quantum state. This just allows for us to go into a temperature which is on the order of 60 degrees centigrade. Instead of being 3000 Kelvin or 3000 degrees centigrade at that stage, there is no difference. It is just 60 degrees centigrade. So then it allows us to actually really pump harder, and then having an omega, other groups for cooling these particles have omega which are on the order of 100 kilohertz. By doing this, it gives an advantage. Experimentally, we're always looking for advantages. Instead of having 100 kilohertz, we can go to tens of megahertz, a factor of 100 improvement. Yeah? So, and then now we have to cool down our particle, and we have to cool it down. When I say cool it down now, forget about the internal temperature. That is already taken care of. We had to cool down the center of mass motion of the particle. For that one, we use two approaches. One is parametric, and the other one is feedback cooling. Parametric is basically, if you remember when we were kids, or in my case, even now, I'd like to go into a swing, right? And every now and then I ask my wife, can you push me? Yeah. And then you have to push at the right time. Because if you push at the wrong time, the swing doesn't move. Yeah. What is to push at the wrong time? Well, when the swing is going the fastest, you push. And you push against the motion, yeah? That is basically parametric cooling. You push at the wrong time. As the particle is moving, you are going to cool it down by pushing. If it is moving, you push it. If it is not moving, don't do anything, yeah? So what you're going to be saying is, well, that should work, right? Well, except that you have to detect that it's moving. And then detection efficiency means, well, your particle is scattering this light, the trapping laser is being scattered by your particle, and that is basically telling you that the particle is moving, right? And that is what you use. But then you have an actual detector. The efficiency of the detector is not 1, is less than 1. So what happens is that every now and then your particle is moving and you don't realize that it is moving and you don't push it. So this tells you that you don't have a perfect cooling scheme using this approach. Yeah. The other approach that we have is what we call is passive, and it is cavity cooling. And so you basically put your particle in a cavity. And for reasons I'm not going to start explaining, this particle likes to go to an antinode. But what happens is that since this particle has a finite index of refraction, if it moves away from the antinode, then the fineness of the cavity decreases and becomes very lossy, and then the particle gets pushed back to this antinode scene. You can really see movies from this. I decided not to load the movie in this one, what happens with this particle, but this is basically, and there are different approaches for cavity cooling. You can pump your cavity, or you can just use the scattering from the field, from the external field in order to populate your cavity. So again, there are different approaches. I want to move on just to show how this is implemented. There are, again, this is all optical, and this is what basically this parametric cooling means. Basically, what you do is you change the intensity of the trapping laser. If the particle is moving away, you change the intensity in such a way that it makes the potential stiffer, moving it to the center, and so on and so forth. So all these are implemented. But just to give you an idea, this typically, when you do parametric cooling, you can cool down to basically millikelvin, which is not enough to get into the quantum regime. I mean, 1 millikelvin is too high a temperature in order to be KBT to be much less than h bar omega naught. It is basically on the order of h bar omega naught when you have a frequency of megahertz. The system that it is actually used is complex in the sense that you need to have a cavity cooling control. You need to have a feedback, parametric feedback control. And here what we have is you have the trapping mechanism, and then you have to move this particle and put in the antinode of your cavity. And it's even more complicated than that. Basically, what you have to do is you have an atomizer where your dots are. This is in a high pressure system. So and then you trap it, and then you have to move it. So you trap your little particle in an objective, and you know that it is trapped because you are measuring that there is a finite luminescence, photoluminescence there. And then you have to move that from this high pressure to a very ultra high vacuum system without losing the particle. And that is tricky to do, but it's doable. And I mean, it's doable with a yield which is probably 50%. So you trap a particle, you try to move it, and it becomes this loss. So you have to trap another one, and so on and so forth. But then you move it into your high vacuum system, and then you put it into high vacuum. And basically, the particle there will stay for a long time unless there is residual gas, and one of the residual gas molecules hits your particle, and your experiment is completely gone, right? I mean, you lost your particle, you have to start all over, yeah? But then again, I mean, you can have these particle traps by a good amount of time. I will say maybe a day or so, and then eventually something happens and you have to start all over. But okay, you have a procedure and a protocol, and then you cool it down. We can cool down to temperatures on the order of microkelvin. Just to give you an idea, don't pay too much attention to the parameters, but just to give you an idea what happens, right? There is always a trade-off. There is a trade-off. Remember, I told you that you have a detector that has certain efficiency. Then, of course, if you use more light, then you have this curve here, which is with stars. If you use more light, you can detect better the motion of your particle. So you say, well, increase the amount of light that you are sending to your particle, and then you will continue on this line until there is something that you cannot go against, which is the 0 point motion of your particle because it's a harmonic potential. That line is here is 1. This 10 to the 0 is basically the 0 point motion. This graph and the parameters are selected in such a way that this crossing point is basically 0 point motion. Yeah. But there is a trade-off again, right? I mean, you have a laser. So if you increase the light, your laser is a coherent source that has short noise. And then you have what is called the back action. So you're pushing your particle. You have a constant intensity. But this constant intensity has 1 over square root of n fluctuations. And this is basically a back action that is going to make your particle move. As you increase the power, this is this line that we have here that basically is telling you that well, if you keep increasing the power, this actually the noise will start increasing. And there is a sweet spot. And this sweet spot depends on the efficiency of your system, which is eta. So if you want to go down this curve, you have to increase the efficiency of your detector. If you want to move to the left, you have to decrease the gamma is the losses from your system, or increase the radius for your particle, or increase the omega of the energy of your electromagnetic radiation, similar for going in the other direction. So just to give you an idea that you really, once you want to go into a quantum measurement, you have to take into account that all the interactions associated with your method. Very briefly, these are basically the things that you can do, and the temperatures that you can get, as I was saying, with parametric cooling alone, you get 10 to the -3. With parametric plus cavity cooling, you get to microkelvin energies. And then if you do that, what you can get is that you can get this curve for Yukawa interactions that will go much better than before. And let me just jump and very briefly tell you there are better ways of detecting motion. This motion that I said before is given by the standard quantum limit, which is basically the Heisenberg principle. We're trying to measure position and momentum at the same time on our approach, and you cannot do better than Heisenberg limit. Yeah, but there are other methods better than that, and you can improve that. Interesting enough, everything that is shown in here is quantum, but there are regions which is called non-classical region, meaning that you are going beyond the standard quantum limit. Yeah, the standard quantum limit will be this red line. Anyways, just very briefly, can we detect gravity using this approach? This is basically the gravitational field of an infinite cylinder. It can be done for a finite cylinder. And then what we have is we have a little sphere, which is the sphere that is being trapped. And then we have this array of cylinders. And we're going to move this array of cylinders with respect to this particle. So this force that this particle is going to be feeling along the z direction is going to be oscillating, becoming stronger when you are right on top of the cylinder, smaller when you are here with in between cylinders, and then you have this driving force. And the question is, can you measure it? This basically what we will do is, well, again, we put our particle in the quantum regime, we put it in the ground state, and what we can do now with this oscillation is we can drive gravitationally the particle from the ground state to the excited state. And then that is what we're trying to do. Can we do a pipe pulse with this gravitational interaction? And the idea is it works. Yeah, we can calculate a Rabi frequency, which is going to be this expression here. We can get into the details of that, but just to give you an idea, for a 50 nanometer particle, so the mass of our particle here for a 50 nanometer particle is on the order of 10 to the minus 18 kilograms. R will be the radius of the cylinder on the order of 100 microns. Rho is the density of the cylinders on the order of 10 to the 4th kilograms per cubic meter. G is G, H bar is H bar. You get that this Rabi frequency is 10 hertz. And in principle, you'll say, well, you can do it. Well, yeah, but you need to have coherence for things that are going to be on the order of 10 milliseconds, and that is basically, 100 milliseconds, and that is not happening, right? We need to enhance this by 5 orders of magnitude, or which basically means isolate our system, create a system which does not decohere for 5 orders of magnitude better. So we're far away from it. However, we can still go back to our to our current here, and then improve over the standard quantum limit by a lot. And the way of doing that is, instead of just having going back to this cylinder, instead of just having one distribution of cylinders, we're going to put two distribution cylinders, because what we're going to do is we're going to produce a two-color, a wave which is a gravitation based, one which is right below the excitation, one which is right above the excitation. Nothing happens at the frequency of the excitation, and we do this two-color, and then basically nothing is moving at the frequency of the transition, and then that allows us to basically have this pattern that we actually, this is actually a sample which is put in a lathe, high precision lathe, in order to produce these transitions. And then what we do is we tune these for different lambdas and alphas, and that will allow us to bring this curve by basically 3 orders of magnitude more. So we're actually quite optimistic that we'll be able to do this hypothetical correction using this overall quantum approach. So summarizing, we do have quantum sensors, which is this particle type in a harmonic potential. We have tricks in order to do this better. We are confident we'll be able to measure the quantum friction and improve these limits for these Yukawa mediators, or even for non-Yukawa ones. It's not sensitive to Newtonian gravity yet, but I think that we have an idea on how to start probing this, and eventually, when we get an enhance reduce the decoherence time to, or actually increase the coherence lifetime to something which is more measurable, I think we can have something that will allow us to really go into this probing if gravity itself is quantum in nature. And it is a lot of fun, and the lab is a great playground. I mean, well, I mean, I wouldn't say that it's all roses. Yeah, I mean, there is an experiment. There is a lot of frustration, but there is a lot of tinkering that we can do and have ideas and go to the lab and try them on. So thank you for the invitation, and I hope it was useful just to give you an idea of what kind of approaches we use in our lab. Thank you.
Thank you so much.
A few questions. Anybody? Yes.
It was about maybe 4 or 5 slides ago, but with the pi/2 pulses, what kind of time frame does that occur in? Like, how long or short does that take?
Sorry, pi pulses with gravity?
Yeah, so when we were going from the ground state, and then there was the pi/2 pulse. It was the question. There was a question about the laser earlier.
Yeah. So the question is how long does it take to produce a pi pulse?
Yeah.
Basically, what this omega tells you in here, right? What this omega tells you is, given an interaction, a Rabi frequency tells you what is the frequency in which you put an interaction, and at what frequency this will be swinging from 0 to 1 and back to 0. Yeah, so these will be oscillations in which you start with your state in 0, and then after a time, which will be 2 over omega. So the period will be 1 over omega. So at half the period, what you will do is you will have transformed your 0 state completely into a 1 state. That is what a pi pulse is. The problem is that for this particular interaction, the interaction is not strong enough, right? You have G here, which is weak. So if you try to do this with that, this frequency of oscillation between the ground state to the first excited back to the ground state is just too low. So you need frequencies which are going to be much higher. So just to give you an idea, so if instead of doing this with, not that you can do it, but if instead of doing this, instead of with gravitation, you were going to be doing it with electrostatic interactions, then what happens is that instead of G, you have, instead of 4 pi G, you have 1 over epsilon naught. So then your interaction is much stronger, right? And then you will have that you can drive these back and forth between the ground state and the first excited state at a time that will be much faster determined by this Rabi frequency, which is omega. Does that answer your question?
Yeah, thank you.
Yeah.
Anybody wants to ask about quantum gates?
I have one question here.
Yeah, okay.
I have a question in this slide itself. Now, to measure the gravitational effects, we are reducing every other parameter down so that we can observe these weak interactions. Is there a way to tune the interaction of gravitation so that we can increase, instead of lowering everything else, if we can increase this interaction so we can observe it normally? Is that possible?
Well, let me see if I understand the question. So your question is, can we somehow get rid of all other interactions? So you're going to just be having the gravitational interaction and being able to measure that interaction directly? Is that the question?
Not exactly. I don't want to isolate gravity. I want to tune gravity somehow.
Again, well, if you let's say that you have the interaction gravitational potential, which is the 1/r. So and that one you cannot tune, right? I mean, that one is whatever it is, and the strength of the interaction is g. That one you cannot tune, is weak. So what you can tune is your masses and your mass distribution. Okay. And then you can play smart tricks in order to try to enhance that interaction. So just to give you an idea, suppose that I'm doing a cylinder sphere as an example here, yeah. But looking into this expression, if you want to increase this omega, what you will have to do is you will have to increase basically this rho r squared comes from the mass of the cylinder, and this m comes from the mass of your particle. So you could say, well, I'm going to increase the mass of the cylinders. It is okay, but then what is going to happen is that then you cannot put your particle too close to the center of the cylinders. Or you can say, well, I can increase the mass of my trapped particle. You can, up to a certain extent. Bear in mind that if you increase the mass of the particle, also what you're doing is you're increasing the size of the particle. And and then what is going to happen, the scattering of this trapping laser is going to become more and more and more pronounced. Then it will be harder and harder and harder to get into this quantum regime. So it will be harder to put it down, and it will be harder to have this trapping to have the system put into the quantum system. So there is a trade-off that you had to pay, and you want to do the particle large enough, but basically 100 nanometers is basically the limit of the particle that you can use.
Yes. Okay.
Yeah, one last question, can I ask? Yeah. Have you succeeded, or do you have any plans to put together 1 and 2 qubit gates in your lab so you can establish a quantum circuit of some sort?
Yes, I have not succeeded.
Oh.
Yes, we have ideas. And the idea is the following. Then instead of having just one trap, what we're going to have is 2 traps. So imagine that we have two of these oscillators. That is actually reasonably easy to do. You just have to have a modulator that basically, instead of having your laser going to one spot, it goes into 2, and you can adjust that separation. And then basically what we do, or what the idea is, basically imagine that now we have 2 of these particles, the blue particles, on top of these oscillators, of these cylinders. And then we have the interaction between this blue particle and our cylinders, and the interaction of the other particle with those cylinders. So that is called basically what is called is a mediator. Now, what we want to do is we want to prepare each one of these blue particles in a definite state. So we have a qubit of the blue particle, another qubit of the other blue particle, and then both of them, they are interacting with these distribution cylinders. They're also gravitationally interacting between them, but remember, if this interaction was small between a massive cylinder and this particle, imagine between these 2 very, very small particles is basically negligible, yeah? So the direct interaction is negligible. So basically then, if we can do, assuming that we can drive the system with this gravitational interaction, then we can take a look into, we prepare this system in a pure state, we prepare the other system in another pure state, and then we basically let this interaction run for a given amount of time. And the question now is, are these 2 particles, the 2 blue particles, entangled between them? And then there is no direct interaction between them, right? So this is your quantum circuit, which is basically mediated by gravitation. And then, sorry, I said that my dog will start barking, and there is the dog barking. And then basically what is going to happen is that if we get entanglement between these two particles, then there are predictions that, or there are calculations, if you wish, that is telling you that gravity is quantum. If you have a classical field, you will never produce an entanglement. I was actually discussing this with Ricardo Decca, whom you know very well last week, to basically try to do this. Now, can we do it? No, the answer is no. I mean, I cannot even do it with just a single particle, right? I mean, but yes, this is what we're trying to do. We're trying to have two qubits and mediate with gravity, and then produce experiments that are going to tell us if this quantum, if this gravity-mediated interaction is quantum in nature or not. I wish my answer to you would be yes, because then that would be a fantastic experiment. We're trying to move in that direction. We are not there yet.
Perfect, thank you.
Thank you so much.
Okay, so that's it. Anybody has any questions? Otherwise, we need to thank our speaker.
Oh, I'm sorry, I apologize. Yeah, so thank you for coming and spending your evening with us. We greatly appreciate it.
Thank you.
Okay, thank you.
Thank you very much for your invitation and for the attention. I hope this was along the lines of what you were expecting. And if afterwards you have questions, please ask away. If you want to join the lab, also let me know and we'll work something out.
Thank you so much.
All right, thank you.
Very much. Have a
Good
good evening.
evening. Take care.
Excellent. All right, well, thanks everybody for coming. Oh, really? Yeah.